Have you ever held a compass near a wire and watched the needle move even without touching it? That strange motion isn't magic, it's a window into one of the most powerful unifications in physics. Back in 1820, Hans Christian Ørsted was delivering a lecture when he noticed a magnetic needle deflecting near a wire carrying electric current. This moment marked the birth of electromagnetism. It was the first clue that electricity and magnetism aren't isolated, they're intimately connected. The direction of the needle's deflection changed when the current direction reversed, showing that magnetic effects depend directly on the movement of electric charges. From that simple compass deflection, we've built everything from electric motors to magnetic resonance imaging, all thanks to Ørsted's curious observation. Now imagine a straight wire with current flowing through it. What surrounds it isn't empty space, it's alive with invisible circles of magnetic field lines. The direction of these magnetic loops follows the right-hand thumb rule. If you point your right-hand thumb in the direction of the current, your fingers curl in the direction of the magnetic field. The farther you go from the wire, the weaker the field becomes. And the stronger the current, the stronger the field. This fundamental idea helps us build devices like electromagnetic door locks, inductors, and magnetic field sensors. So next time you power up an electric stove or a relay switch, remember, these spinning magnetic rings are silently at work. What happens when a charged particle, like an electron, moves through a magnetic field? It feels a force that pushes it, but not along its path and not along the field. The force is perpendicular to both. This is the Lorentz force, and it's given by the equation F equals Q into open bracket V cross B close bracket. Here, F is the force in newtons, Q is the charge in coulombs, V is the velocity vector of the particle, and B is the magnetic field vector. The direction of the force follows the right-hand rule for cross product, V on fingers, B on palm, and F points out from the thumb. This is the same principle behind cathode ray tubes in old televisions, or the way magnetic fields guide plasma in fusion reactors. When charges move, the magnetic field bends their path, nature's own invisible steering wheel. Let's say the charged particle enters the magnetic field at a right angle. The magnetic force acts as a continuous centripetal force, making the particle loop in a perfect circle. The radius of this path is given by R equals mv divided by qb, where m is mass, v is velocity, q is charge, and b is magnetic field. That's right, magnetic fields can trap and swirl particles in circles. The time it takes to complete a revolution, called the time period, is t equals to pi m divided by qb. Notice it's independent of velocity. This principle powers cyclotrons, particle accelerators used in nuclear physics. It also explains why cosmic particles spiral through space when trapped in Earth's magnetic field. Now let's expand that wire into a loop. What happens to the magnetic field? It becomes focused, curling in through one side and out through the other, forming a magnetic dipole, just like a bar magnet. Stack multiple loops into a coil and you get a solenoid, a device where the magnetic field inside is nearly uniform and parallel, like tightly packed field lines in a tunnel. The strength of this field is given by B equals mu naught into N into I, where mu naught is the magnetic constant, N is the number of turns per unit length, and I is the current. Solenoids are everywhere, in MRI machines, electric buzzers, relays, and even in scrapyards where giant electromagnets lift cars. That's how nature's magnetic power becomes engineered force. Let's try a real example. Suppose a proton moves with velocity 3 into 10 to the power 6 meters per second, perpendicular to a uniform magnetic field of 0.01 Tesla. What is the radius of its circular path? Using the formula R equals mv over qb, we plug in the values. M is 1.67 into 10 to the power minus 27 kilograms. V is 3 into 10 to the power 6 meters per second. Q is 1.6 into 10 to the power minus 19 coulombs, and B is 0.01 Tesla. Multiplying and dividing gives us a radius of 0.0313 meters, or about 3.13 centimeters. That's how we calculate the bending path of particles in magnetic fields, a concept used in cyclotrons and even in cosmic ray detectors aboard satellites. Let's quickly revisit what we've learned. When electric charges move, they generate magnetic fields, an insight revealed by Ørsted that laid the foundation of electromagnetism. A moving charge in a magnetic field experiences a force, the Lorentz force, that can bend its path. If the motion is perpendicular to the field, the charge moves in a circle, guided by formulas like R equals mv over qb. Loops and solenoids mimic bar magnets, producing directional magnetic fields that are vital in all kinds of electric devices. So from simple wires to particle accelerators, the dance between electricity and magnetism is all around us. I hope this session gave you a new appreciation for how magnetism emerges from motion. See you in the next topic, where we'll dive even deeper into the wonders of moving charges and fields.